Okay, so I think we can start this webinar today. So welcome everybody. See people is joining, but I'm quickly starting introduce today's talk. Today's talk will be given by Professor A.Cavallaro and will be titled Multimodal Sensing for Physical Human-Robot Interaction. I also like to remind you that the next one is scheduled for February 28th, same time, will be given by Professor Axel Jansch from TU Vienna. And I also like to remind you this workshop we are going to organize in ICASP and will be signal processing for autonomous systems. I hope to see you all attending ICASP in Rhode Island in June. Okay, let me quickly introduce today's webinar. So we have with us Professor Andrea A.Cavallaro. The title of the talk will be Multimodal Sensing for Physical Human-Robot Interaction. So Andrea A.Cavallaro, very briefly, is a Turing Fellow at the Alan Turing Institute, UK National Institute for Data Science and Artificial Intelligence, and a full professor at Queen Mary University of London. He's also founding director of the Center of Intelligent Sensing and the director of research of the School of Electronic Engineering and Computer Science. He is fellow of International Association of Pattern Recognition, and he, of course, is very famous in the field of multimedia signal processing. I will stop here, otherwise I fill the full hour just reading his bio. So, Andrea, the floor is yours.
Thank you, Lucio, and thank you very much for the invite to present at today's seminar series. I'll share the screen, and please let me know in case there are any issues. All good?
Yeah, perfect.
Fantastic. So again, thank you for the introduction and the invite. I'm very pleased to present our work on multimodal sensing for physical human-robot interaction. And when I say we, I mean people in my group, but also partners of a consortium that is called CORSMAL. There are labs from Sorbonne University in Paris and EPFL in Switzerland. The idea of this talk is to provide you with an overview of the activities we have done and the objectives we have achieved with this project, and share a lot of data and a lot of code. And I hope to be able to invite some of you in participating in our challenges. So the main goal of our work is to be able to create synergies between the recognition of objects and manipulation of objects by human, using the sense of vision, sound, and touch. And we don't want to do this in isolation. We do this with the community, with the idea of favoring reproducibility. And what I will go through in this talk is technical aspects as well as organizational aspect in how to favor the development of research in a certain topic, and in particular, human to robot interaction through a physical object. The specific topic we looked at in the project CORSMAL are the ability of a robot to understand the intention of a human and grasp an object that is offered by the human. And the robot knows nothing about that object. There is no information about the size, no information about the material, no information about the stiffness, no information about the weight. And all this has to be inferred by the robot while the human is manipulating that object. So it's a problem that goes much beyond what is the current state of the art in computer vision, where you're trying to recognize a pattern in an image. Here we are looking at the patterns, but also at the behavior of the human, at the sounds that are generating when the human is manipulating the object, in order for the robot to understand what are the physical properties that will infer then on the object, to then predict where to grasp it and with what strength to grasp that object. The main phases of this problem have been divided into three: the grasping by a human, the handover, the dynamic handover between the human and the object, and then the delivery of the robot to a specific position. In the first part, we have human manipulation with the interaction between the object and the content of that object and the human, then the dynamic handover, and finally, the robot manipulation part. And in particular, in the human manipulation part, we're looking at 3 modalities, vision, sound, and touch. And for robot manipulation, we're looking at sound and touch. And I will mention across the talk the data we have produced that you can use, the models we have trained that are open source, and the results we have obtained. So here is an example of human to robot handover. So the idea there is that we have a cap, in this case, a pretty visible cap with content. The robot doesn't know about the content of the cap, and go grasp the object with the idea of not crash it, not let it fall, and making sure that the content isn't spilled. Here is another example of a robot getting an object from a human, and I will let you observe so that you get a sense of the challenges in this task. So the idea here is to make sure that the robot can deliver the object at the desired position without spilling the content, without deforming the object, and without letting it fall. So there are a number of challenges we have to address, and primarily the ability of the robot to determine the physical property of the objects that are unknown. So we have no information about the object. We have no prior models about the object. And again, what we have tried to do is to use multimodality, vision, sound, and touch, and to generate protocols, evaluation protocols, data, and machine learning models that are distributed to the community, for the community to be able to improve those models, and then in turn distributed back for improvement by the overall community. The idea is that if we have protocols, data, and models, then we will be able to compare, improve, and then reproduce the results themselves. And again, as I mentioned earlier, I do hope that today some of you will be incentivized to download the data sets, download the model, and improve upon what we have achieved so far. This is a list of items we have generated so far with the project. On the left-hand side, you have the links to the benchmark we have developed. These are all paper where we describe how across different laboratories in the world we can reproduce the behavior of humans in a way that we can compare results across sites. So we have a definition of what an handover is, where the objects are grasped, what type of objects we have, objects that can be purchased through Amazon easily across the world. And we have also distributed a baseline algorithm. So if you have a robotic arm, then you can download the algorithm and replicate what we have seen in the previous videos in your lab. In case you haven't got a robotic arm or you haven't got access to one, we've also developed a simulator that allows you to have an end-to-end system, but with the end part, with the handover part simulated with a simulator. We have also collected and distributed a number of data sets, some simple image-only data set, video data set, and audio-visual data set, and tactile data sets as well. And I will mention a bit more about this. And what is also interesting for the community is that we have a large number now of machine learning models that have been trained and are available for you to download and to improve. The improvements can then be compared in a leaderboard that we have on the very right-hand side of the table, where you can decide which specific task to address. You submit the results, and then those results will be updated on the leaderboard. So it's going to be extremely easy for you also to generate tables for your papers and for your comparison, because data are already available in the leaderboard themselves. So I would encourage you to play with the data and play with the model, and hopefully you will score very high up in the leaderboard. In terms of models, here is a list, a non-exhaustive list of models we have developed, trained, and distributed for this task. We went from audio classification of the content of food container and drinking glass, and I let you hear some samples of this data set. So here the idea is to be able to understand through sound the amount of content that is poured into a container, so that the robot is able to predict what is the force to be applied to the object itself, because the physical properties of the object will change depending on the quantity and type of content. Then we looked at how we can use a certain type of features to increase the robustness to distribution shift when we have different type of data, how we can use adversarial training, and I will mention this task later on, to improve the classification of the filling level of a certain container. And then we use multiple views in order to recover the 3D shape of the object themselves. On the robotic side, we did quite some work, especially the partners in Lausanne, looking at how to interpret the behavior of a human in order to infer the weight and the fragility and the filling level of the object, as well as looking at what type of inferences can be done when a robot is manipulating an object and the content within an object is changing position and therefore generating sounds. So a number of this will be addressed later on, and all the publications are available at the link at the bottom. And all publications have also got available the code to replicate the results. The simpler dataset we have is the CORSMAL container dataset, which is characterized by a number of containers of different types. You see there that especially when you go from 5, 6, 7 above, you see transparencies and quite some challenging shapes. The idea there is to have an entry-level task for the ability to recognize the dimension of the object and to segment the object from the background. So affordances for the robot can be defined. And we provide here RGB, depth, and stereo infrared data together with annotation. The second dataset is the CORSMAL container manipulation dataset. You see here that the sensing setup is slightly more complex. We have 4 cameras, 1 on the manipulator, 2 on the side of the robot, and 1 worn by the user, and also a microphone array that is capturing not only the sound itself, but also will provide information for the direction of arrival of the sound itself. Here are some examples of data we have collected. So here is an empty box, and from the type of sound that is generated or not generated by the shaking, the robot shall be able to infer that the box is empty and therefore be very careful with the grasping operation. So here we have a series of situations where a human is manipulating a container, and based on this information, we want the robot to be able to infer the physical properties. In here, instead, we have the robot manipulating the object, and we want to be able to use sound information to anticipate the change of mass distribution of the object to avoid slippage. And in case slippage is predicted or detected, then the force of the robotic hand shall change. So in here, as I mentioned earlier, we have audiovisual and tactile data, which I think is one of the very attractive aspects of the data set the CORSMAL project has produced. Here is an example of audiovisual data where we have the subject pouring content on the glass and then handing it over to the robot. And for those of you who haven't got a robotic arm, we can use the dataset on the left and then integrate it with the simulator we have developed for you to be able to have the end-to-end pipeline in software only. At the beginning of the project, we had to come up with a specific benchmark in order for people across different labs to be able to compare their results. We came up with three set of scores: the perception scores, the robotic scores, and the global scores. If you're interested in the specific details, the link at the bottom has got the paper and also the link to the code that allows you to reproduce end-to-end the entire pipeline for CORSML. One of the interesting aspects that we didn't anticipate at the very beginning is that we have to define quite some trivial or apparently trivial aspects of the benchmark. For example, what type of grasp people are allowed to do in order for laboratory A to compare the results with laboratory B. And in the paper, you will see a number of combinations of grasps and positions of the changes of hands between the robot and the human in order for your results to be comparable in technique with those of other laboratories. So it was a very time-consuming effort, but I think now a number of places in the world are using this as reference for human-to-robot handover benchmarking. And you can find the data set, the code, and the link that you see in this page. Just to summarize where we are, you have now available code and methods to enable your robot or your simulator to determine the position and the physical property of an object so that a robot can go pick it up and place it in a desirable position in the space. Now I'd like to focus a bit more on some of the techniques we have developed in order for our end-to-end pipeline to be able to deal with data that are not that common. Right? So the data we have seen so far are not really your traditional ImageNet or COCO data. They are very specific. They've got very special characteristics, like if you can see here my pointer, you will have a transparent glass plastic cap over a very colorful background, a very challenging scenario. Here you have a cap that is substantially occluded. In here, you wouldn't be able really to determine the amount of content you have, whether in situation like here and there, you'll be able to do it. So we wanted to see how we could use already pre-trained models and then refine their training in order to improve the filling level estimation. We consider 4 types of caps and 4 drinking glasses with variability in transparency and shape, and 4 levels of filling: no filling, half or full or unknown filling, and 3 types of content. And we looked at a number of ways in which we could train based on the CORSML container data set. So standard training, adversarial training, or standard training followed by fine-tuning, or standard training followed by adversarial fine-tuning, or adversarial training and fine-tuning, and adversarial training and adversarial fine-tuning. And it turned out that the best combination is to use adversarial training in the source domain and then fine-tuning in the target domain. So specifically, we looked at this winning strategy, which is to use a source domain, like for example, ImageNet, with adversarial training, so adversarially trained model that then is refined in the last layer with the specific data set. And this approach turned out to be the most successful in terms of prediction of filling level classification. We then looked at other ways in which we could improve the way the models were trained with data augmentation. And we came up with a number of spatial domain, color domain, and spectral domain modification of the input data that came out to be particularly effective in improving the way the robot would be able to determine the physical property of an unknown object at test time after this type of training. So we used a mixing strategy that manipulate the input data spatially in color and with spectral information, and that turned out to be particularly successful. The third case I want to mention is in this case using 2 views. Again, we have no prior information about the specific object, and using the 2 cameras, we want to be able to determine the 3D shape of the object. And we use a combination of 3D and 2D shape fitting, starting from image segmentation, where the system goes from the image plane to the 3D space and back, refining the results from the two views in order to determine what are sample points on the actual object in 3D. So here are some examples. The assumption here is that the object is upright vertical, and there is circular symmetry. We are closing in with a certain starting point, as you see there in red, and closing in towards the result of the 2D masks projected on a 3D common space, and then reprojected back to determine the error. And what you see in green is the final estimation of the 3D shape of the object that the robot in this case is meant to grasp. And this result is coming from an iterative 2D to 3D approach. And you see here a transparent bottle, and there is convergence. And the steps you're seeing is the continuous projection back and forth between the segmentation masks in the two views and the estimated 3D space. We have distributed this code, and the community has already started using it and improving it on a number of tasks. The first task is fill-in level classification, the second is fill-in type, and the third is the estimation of the capacity of the container. All this to determine the mass, and therefore to determine the type of strength the robot shall grasp the object with. In addition to that, we have two additional tasks, which are container mass estimation and the dimensions of the container, the estimation of the dimensions of the containers. And all this was used in a number of international challenges, for which now we have a pretty long leaderboard. And I do hope that after today's talk, a number of you will be looking at those data and trying to improve on the currently existing methods that are available on the COSMA website. This gives you a summary of the institutions that have been participating in the challenge. And we had challenge events at ICME, ICPR, and ICASP. And we will be organizing one other challenge in the near future. And if you're interested either in joining in as organizer team or participants, please do drop me an email so that I can provide you with more information. I wanted to give you a sense of the type of algorithms that are available out there from the community. So only one of the algorithms mentioned here are from the consortium and is the one in gray, which is what I showed earlier, the ability of the robot to determine the 3D shape of the object. And then all the others are models that are available online for you to use and have been generated by participants to the challenge. And some of those are looking at the capacity estimation, some of those are looking at mass estimation, fill-in level estimation, and so on and so forth. So this will give you a sense of the amount of code that is already available out there for you to start from and improve upon. This is a sample of one of our leaderboards where you see the type of results we are at the moment. So certainly there is room for improvement up to 100% of the score. And you see that there you have a number of methods that are available also for you to compare against. So as a summary of this project, before I move on to the next two topics of this talk, we have generated a number of tools, data sets, and models for the community to use. I do hope that you will join our community and you will participating at the next challenges we will be organizing. Now, I'd like to go back to the initial comments we made at the beginning regarding the multimodality of this talk. So we are wanting to use multimodal information to achieve a certain goal. In particular, I would like now to look at how we can relate information of the same physical phenomenon across observation modality in order to model or to explain an event, which is what we have seen so far. We try and use audio information combined with visual information to determine the physical properties of a specific object. And what I'd like to describe now is a method I'm particularly attracted to, that Vandana in our group developed, that aimed at using one modality available at training time, but not available at test time, to improve the performance of the other modality, which is available both at training time and at test time. Let me explain a bit more about this. So the question we asked ourselves is, what if at test time one modality is unavailable or severely degraded? So how can we exploit training so that the remaining modality at testing is stronger than if it was trained in a single modality? And this was IEEE's work in 2021. So the solution we looked at is multimodal training to improve the uni-modal performance. So meaning that we can have a smaller footprint classifier on board of the autonomous system that was training benefiting from multiple modalities. How did we go about this? So we wanted to use multiple modality through cross-modal translation in order to improve what the single modality can do at test time when it's used alone without the other modality. In order to do that, we forced the latent space of the modality available at test time to be aligned with the latent space of the modality that was available only in training time, with the assumption that the modality that is not available at test time would be the stronger of the two in terms of ability to represent the phenomenon we want to highlight. And here I'm showing the pipeline we looked at. So up here in one color, we have one modality. Down here in the second color, we have the second modality. So imagine you have here audio information, visual information, or vice versa. And we have then a classifier that is operating only on one modality, but it was trained here using both modalities. Let me dive into this problem a little bit more. So we have in here on top an input of one modality and the output of the second modality. Let's call this a intramodal autoencoder. At the bottom here, we have as input one modality and as output the other modality. So we have here a cross-modal autoencoder. And at the bottom, we have a classifier, a regressor, which is the task we are interested in. So at test time, we do have only the input here, exiting there. And at train time, we have the information from the two modalities and the output. In terms of loss functions, for the intramodal autoencoder, we have used, for example, video, and we minimize the loss between the output of the intramodal autoencoder and its input. So we're trying to replicate the signal that is input in the output. Then for the other modality, we forced in training the output of the intermodal autoencoder, the translator, to be as similar as possible to the input of the other modality. So here is where we are forcing the encoder of the modality present at test time to be as similar as possible to the output of the encoder, of the intramodal encoder. And the third important loss is that that is forcing the latent features of the strong modality and the weaker modality to be aligned. And finally, we have a fourth loss, which is a traditional loss that compare the results of the classifier or the regressor with the ground truth. We demonstrated in an audiovisual emotion recognition problem, that training the uni-modal classifier with a multi-modal training strategy based on those 4 losses is substantially improving the results of a uni-modal classifier trained on the very same modality. And I think there are a number of applications that will benefit from this type of approach. The last topic I'd like to cover is what if the acoustic noise is very strong? And in particular, what if we decide to have an autonomous system like a drone that is capturing audio information from an environment and is trying to make sense of the content of that audio and to determine the direction of arrival of the audio. We have developed a number of prototypes that have looked at how to combine sound information and visual information in order to have awareness of the scene around the drone while the drone is operating. So the drone is generating a substantial amount of noise. And what we want to be able to do is to extract relevant signals from this noise, enhance them, and be able to interact with a particular user or to locate the position of a user. This is the very first prototype we designed, nothing particularly fancy, or at least certainly not fancy as the latest one we are collecting data and testing on with, but we are very, very happy of this initial method that allow us to characterize the type of sounds and signals we were interested in. This is Lynn, who has developed the initial models for this problem. And what I'll show you here is a video and the recording of the drone, in this case on a tripod, just to give you a sense of what is the input sound. And then in the next video, I will show you the result of the cleaning of that sound using a multi-sensor array technique. So this is the original sound. And this is the result.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19.
So here is the ability of the system to determine how to extract the relevant signal, assuming that we have a number of microphones that exceeds the number of sound sources. In this case, the sound sources are 5, the speaker and the 4 propellers. We have generated also for this type of problem a data set that is available for you to use. The link to the data set is at the bottom left. Is an audiovisual data set, so we have added a camera to the microphone array, and you see there 2 configurations we have used in order for the results to be reproducible. We have used a loudspeaker instead of a speaker, so that with different configurations, we have always used the same type of sound emitted by the loudspeaker. And I would like to conclude by showing you a particular example of how you can use multi-modal information in order to extract relevant signals in a particular direction. And in this case, when you have multiple speakers talking simultaneously, saying the same text in front of a system like the one you have in here. Okay, so you can see here that by using visual information to localizing the sound source allows us to separate simultaneously speaking speakers that are uttering the same sounds and separate them one by one. So to summarize, we have seen a number of problems going from human to robot handovers to training a uni-modal system using multiple inputs at training time, to how to generate relevant speech information out of a very noisy mixture between speech and ego noise from the drone. The people who have been working on these problems are listed there, and I do thank them very much. Are people from here in London, from FBK in Italy, and from EPFL in Switzerland, and I do thank them very much, and I thank you very much for your attention.
Thank you, Andrea. Thank you. Okay, so I think we have time for questions from the audience. Can I ask you, everyone, if you have a question, feel free to open your microphone and put directly the question to Andrea, or if you prefer, you can also write your question in the chat, as you prefer. Well, let me start with the curiosity myself, as we wait for the audience to think about their question. So about the first problem you showed, the one of estimation of levels for human-robot handover. So my question, sorry for maybe is a little bit stupid, but anyway, seems to me that of course is a very hard problem to solve. Otherwise, we are not trying to solve because it's too easy. But it seems to me that, of course, if you don't know the exact, let's say, the material that is inside the can or the glass, it seems to me very impossible to find the weight in such a way that the autonomous machine, the robotic arm, is able to grasp correctly the bottle or whatever. So, for example, of course, if you have a glass of water, we'll have a certain weight. If you have a glass of I don't know, cotton or very light material, we have a completely different weight. And basically, you are not able, even us humans, are not able to find out the solution with only our sides and maybe here, of course.
You know, that's a very relevant question, and was actually one of the initial motivations for this project. So it's how can we leverage information from multiple modalities to achieve something that with a single modality would be impossible. So here we looked at two types of complementary information. So the first one you saw in one case. Perhaps I can go back to the slide so that we see what I'm referring to. Yeah, here it is. So in this top right figure, you see a human hand that is instrumented with tactile sensors. And those were experiments that one of the partners of the project ran in order to understand whether by looking at a mixture of movement data and grasping data, it would be possible to infer the filling level, the amount of content in a container based on how the acceleration and the movement was characterized. That to understand the filling level. Then we used audio information to understand the type of material based on the sound that the contact between the material and the surface of the container we're making. Then there is an inference of the physical property of the content itself. If you combine that with training and also with the estimation of the measurements of the object, then you can have an inference on how heavy that object is likely to be. Of course, we are assuming that the human is not cheating in their movement, and we are assuming that we have seen enough. And the idea of the human grasping behavior on the top right was to create models that were able to predict based on the behavior of the human how likely the object was to be half full or completely full or empty, based on how dynamically that object was manipulated.
Okay, thank you. Okay, so
and we are Lucio, we are always looking for counterexamples. So if you can create a few examples where, I don't know, you're cheating, and you can record the videos with an iPhone or with any cameras you have, and then we can try them and see how well with the simulator we can do it.
Okay, very good. Okay, so there is a question on the chat from A.Cavallaro. Is asking, how is guaranteed that the latent space in the middle of autoencoder in the test training time is representative for test time?
Oh, that's a wonderful question. Yes, very good one. Thank you. Well, guarantee, no guarantee, in the sense that we do hope that the training data set is sufficiently representative of what is happening at test time. So if the training data set is such that there is representativeness, then we can have that type of certainty or confidence. In case there is an enormous distribution shift, well, in that case, like in most situations in machine learning, it will be just wishful thinking to hope that we can guarantee anything in that case. So if we know the context of use and we know that one of the modalities will not be available, either because we want to have very small footprint on board of the autonomous system, or because perhaps one of the sensors is not working well, then if we know the application scenario, then we can have an appropriately representative data set, and that has been demonstrated to work very well.
Okay. Yes, another question on the chat. So it's about sensitivity to adversarial attacks in one modality at training time, leaving audio of wrong object or manipulated audio.
We're working on that. We haven't got a meaningful result yet, but we are trying to have multi-modal attacks on this type of systems. We have a number of papers out there on adversarial attacks on audio, on video, and now we're looking at this type of situations where we have multiple modalities. Hopefully, we'll have some results to share sometime soon.
Okay, thank you. Any other question from the audience? Otherwise, let me put another one from me. So about the second topic that you show, you talk about audiovisual, so classification of emotions, if I
yes, yeah.
But sorry, if you can be a little bit more specific, because I didn't get so well the application, say so.
Yes. So the application for this work, let me get to the slide so that I can show you the reference. So this is the reference. The application was the following: given videos of people interacting, how can you infer what is the level of valence or arousal of the people involved in the conversation? And what happens if you're using only visual information, so gestures and face movement, or audio information, when you can train with both modalities? So the specific case we have used as data is this one. We have videos of people talking. You train in a supervised way with the entire video, and then you test on different data either with only audio or with only video. And we have done a number of exercises to understand whether there was really a contribution of actually what we were most interested in is not just one modality switched off and the other one working. It was a more exciting problem, which is assuming that you know that for a certain problem, one of the two modalities is preferable, if available, it's better performing. Can you use that modality in training to improve the performance of the worst modality of the two? And the answer, at least for the specific case of audiovisual emotion recognition, is yes. So if you can use, for example, audio information to improve the video or vice versa.
Well, an example of degraded audio could be also the one that you show in the last part. Of it. So, assuming that you can detect that one modality is degraded and therefore you switch it off, then in this case you can do it. We have done other work where we were instead using both modalities, and over time we were using the confidence of one modality to modify the parameters of the classifier of the other modality because the conditions were changing over time. And that's also other work we have done together with people at FBK, Alessio Brutti in Italy. Okay. And then, so again, about the same topic. So you basically are using, in this case, only audio and video. Have you ever tried or thought to use other types of sensors, especially for emotion? Maybe not in the case of you're talking about, but maybe you're detecting emotion of somebody that is in a more medical related application, let's say somebody that is talking to a camera, but also with some other sensor. Have you ever tried or thought to use other sensor for that?
We haven't directly. So we have colleagues like Yanis Patras working on this type of problems. But I was trying to understand whether anything would prevent a cross-model training for example, physiological sensor. No, in principle, I don't think so. So if you had annotated data for training, I think it would be actually a pretty interesting problem to look at if you have the data. The code of this work is available if you want to play with that. Mm-hmm. And certainly could be a very nice use case for this type of training.
And you think it's also pretty adaptable to other types of sensors, or?
Well, I mean, there will be time series, right? So if you have, for example, any physiological sensor that is a reasonable time series, that could be somehow comparable to audio. I don't think there would be a huge delay. Because one of the problems is the alignment of the two spaces. Sure. So as long as the occurrence of the phenomenon you're observing is appearing with the same type of delay or anticipation with respect to the other modality, I think that it could be really tried as it is.
Okay, thank you. So, other questions or curiosity from the audience? Okay, so I think if no more question, I think we can thank again our speaker today. And thank you, Andrea, and thank you all for attending. And see you hopefully next month.
Thank you.
Thank you. Thank you. Bye-bye.